Thank you, Trey. Thank you very much for the invitation. I'm really, really excited to be here. It's really pleasant to see the people I haven't seen in a long time. Thank you very much. It's also a great chance for me to tell you about what we've been doing in Villetaneuse. So Villetaneuse is a university just north of Paris. And this is our group. The work I'm going to be presenting today is mostly the work of Aurélie Depaz, who is finishing her thesis with us. Amodsen Chotia and Arijit Sharma. So Amodsen is here and Arijit is here. I've been two postdocs in our group, and they really contributed a lot to this work. And for this specific work, we also had a very nice collaboration with Luis Santos, who is in Germany, in Hanover. So he did lots of theory for us, and along with Paolo Pedri, who is a member of our group. And the permanent members of the group is Olivier Gorsex, Étienne Maréchal, who is here, and Laurent Vernac, who is here. And we were recently joined by a new PhD student, Bruno Laburthe-Tolra, who will participate in our experiment. So before I start, so I will tell you about the magnetic properties of a dipolar condensate, but before I start, I would like to advertise the cold atom activity in Villetaneuse, who is in fact growing slowly, but now we have 5 different groups, 5 different experiments. We have a rubium BEC in an RF-dressed magnetic trap. The project is led by Hélène Perrin, where they studied 2D physics and also ring physics with the BEC. There's a project which is to do a sodium BEC on the chip by Aurélien Perrin. There's a group who studies metastable atoms flying by nanostructures to do atom interferometry or atom surface interaction studies. And our group is studying both chromium dipolar gases, dipolar BEC. We also recently had a Fermi dipolar C of chromium atoms, which I will briefly detail, mostly to study magnetism. And because we were interested in this magnetism studies, we also start a new strontium project who will be led by Martin Robert de Saint-Vincent, who just joined the group. So I'm involved in both these projects, and the talk is going to be only about the chromium dipolar gases that we produce in our group. So as I said, I will try and study magnetism. So lots of our ideas and concepts come from the solid state community, of course. And one of the reasons why we do this is that there's lots of open questions for the study of strongly correlated electrons in solid state physics. Some of them relate to the quest to understand high TC superconductivity, and some others relate to the problem of the frustrating magnetism, so which is described here. For example, if you have two classical dipoles like that, and they interact with a spin-spin interaction, you don't know which spin to put here to lower the energy. There's also open questions in spin liquids, disordered spin liquid states. And all this physics is studied in solid state physics today. And in condensed matter, the effective spin-spin interaction is not a dipole-dipole interaction the way we have in our experiment. It's an effective spin-spin interaction which arises due to exchange interactions. So basically, the simple way to describe it is the following. If you have two spin states identical in two different lattice sites, this spin state here cannot tunnel because of the Pauli exclusion principle, whereas if they are in opposite spin states, this kind can tunnel, lower its energy, interact with the other guy, and come back. This leads to a so-called super exchange interaction, which scales as the tunneling square divided by the on-site interaction energy. So this kind of simple picture gives rise to an effective spin-spin model for the description of the magnetic properties of the material, which comprises an Ising term, some kind of elastic term, S1z, S2z, and an exchange term where the two spins can actually flip-flop and exchange their spin excitation from one site to the next site. This is known as the Eisenberg model of magnetism, which is an effective spin-spin interactions between real spins. And as many of you know, to revisit this kind of quantum magnetism has been a hot topic in the cold atom community, and there's many different approaches to study that. And basically beyond this idea, there's the idea of quantum simulation to revisit quantum magnetism. So many of you know many studies in this field. For example, the group of Marcus Greiner has studied spinless bosons, and if you can have an effective speed which is encoded in the orbital degrees of freedom, and he has studied an anti-ferromagnetic spin change this way. There's also, you can also use two spin states of fermions or bosons, the way, for example, Trey does here at NIST. Also, Esslinger or Immanuel Bloch do that. And for example, the people start to see short-range correlations, anti-correlations for spin 1/2 fermions that have been seen, for example, in the group of Tillman-Esslinger. The group of Klaus Zengstock studies classical frustration using a triangular optical lattice. I should also say, given where I am, that you can also study this kind of physics using ion traps called ions, and you can build effective long-range interactions between effective spins with ions, and this is studied here at JQI in the group of Chris. My field belongs to a slightly different field than that. It's called the field of spinor gases, and the idea is that you can have, the atoms can have a larger spin than the effective spin 1/2 that you have usually. So I will study large spin bosons or fermions, either in the bulk or in optical lattices. So this has been studied. This is difficult to describe everything that has been done in this field. It's a field that is now mature, and that has been studied in many places, including in a group of Paul Lett at NIST close to here. So our experimental system is chromium atoms. So relatively long ago now, we had a chromium Bose-Einstein condensate. And this is the signature of Bose-Einstein condensate that we saw in 2007. So it's a S=3 spin. So you see it's a large spin. It's much larger than 1/2. And 2 weeks ago, in fact, we managed to also produce our first very small chromium Fermi C with only 10⁻³ atoms. We'll describe briefly why it's so small. And this is also a very large F=9½ spin. And so our specificity, our interest will be to study magnetism with these two kind of systems, with the main specificity, and I will detail that later in the talk, that there is relatively strong dipole-dipole interactions between the atoms.
Bruno, when you say you have a Fermi C, you mean it's degenerate? Or?
It's T/TF = 0.5. So, yeah. But it's so small, I will show you, but it's so small that it's a Fermi droplet, let's say. So just to describe the experiment, so we produce quantum degenerate gases of chromium atoms. It's a difficult experiment. In fact, the field has been started at NIST here by J. Bayes McClelland, and later, at the same time, by Tillman Fao, who got the first chromium BEC in 2005. And the reason why it's complicated is that it's a metal, which it's really hard to get a vapor out of it. So we need a high-temperature oven. The atoms fly by very fast. We have a Zeeman slower. And the magneto-optical traps that we can build only hold close to 10⁶ particles. So many people work with BECs with 10⁶ particles. Our starting point is only 10⁶ atoms in the MOT. Despite that, you can actually load an optical dipole trap, do evaporative cooling in this optical dipole trap, and produce a BEC. If you want to extend this approach to fermions, to chromium fermions, the natural abundancy is 10 times smaller. So typically, you only have 10⁵ atoms in the MOT. And if you have 10⁵ atoms in the MOT, it's really not promising to reach quantum degeneracy by evaporative cooling, because the process is very non-linear. If you have 10 times less atoms in the optical dipole trap to start with, basically you'll get less. You'll get nothing at degeneracy. So our strategy was to combine few fermions, and many bosons. So basically what we do is we load the optical dipole trap with bosons and then with fermions. And then, in this situation, we get 10⁶ bosons and only 3 10⁴ fermions, because unfortunately there's very little, there's very bad Bose-Fermi inelastic collisions in the MOT. So this looks very bad. See, if I'm starting with 30,000 atoms in the MOT or in a dipole trap of fermions, there's no hope you'll get a Fermi C with it. So the phase space density is 1.5 × 10⁻⁷. There's no way to do a selective evaporation of the bosons, because we work with optical dipole traps, and we have to because of dipolar relaxation. And so we only can combine evaporative cooling, but there's no specific evaporation of the bosons. But still we tried, because you have to try things. And what we see is the first good news is, so we load both isotopes in an optical dipole trap, we reduce the trap depth, and you see the reduction of the boson temperature, and the fermion nicely adapts to the temperature of the boson. Now, if you plot during the evaporation the number of fermion atoms divided by the number of boson atoms, you start with a very small fraction. And as the cloud cools, the fraction remains constant, which means that there's no selective evaporation of the boson. It's a simple co-evaporation. We need the boson because we need some kind of coolant for the fermion, but both are evaporated at the same pace. But there's a surprise here, which we don't understand, but it's nice because otherwise the things wouldn't work, is that this fraction all of a sudden starts raising. So what I believe might happen is that we might be in a situation where the fermions are in fact trapped by the bosons by collisions. So basically, if the scattering length between fermions and boson is so large, the fermions cannot be evaporated from the boson cloud, because while leaving the cloud, it hits another boson atom, and if you reach this so-called hydrodynamic regime, then the fermions can be trapped only by the atoms, the bosonic atoms. And thanks to this feature that we start studying in our system, this is like 2 weeks old, we can reach very, very low temperatures. And this is, for example, one of the first pictures we had of 10 to the 3 fermionic atoms at T/Tf equals 0.5. So this is something that we are very excited about. And we plan to try and study this, study magnetism with fermions now. But for the rest of the talk, I won't talk at all about Fermi systems. I will only talk about boson systems. So, of course, with 10 to the 3 particles, it remains open to see whether the signal-to-noise will be enough to anything, but we'll see. So anyway, this seminar will be mostly the study of magnetism with large speed called bosonic atoms. The system is chromium atoms, chromium-52 atoms, bosons, loaded in an optical dipole trap. And the main idea here is that the optical dipole trap equally traps all Zeeman states. All the Zeeman states see the same potential. And the energy of the different Zeeman states only differ by the linear Zeeman effect. There's no quadratic effect in chromium, only a linear Zeeman effect. And we have 7 spin states. The way we measure the 7 spin states is to do Stirner-Gerlach separation in the magnetic field gradient. So the high field seekers go right, say, and the low field seekers go left, say. And after a long time of separation, we observe the different spin states. So in our experiment, what we focused on was to measure accurately the different numbers in different spin states. And so as a consequence, we work at very low magnetic fields, long expansion times, and we lose all information of the momentum distribution of the cloud when we do Stirner-Gerlach distribution. We only know accurately the number of atoms in the different spin states. And the idea to work with large spin atoms is that we will have access to physics beyond the conventional S equals 1/2 electron magnetism.
Before you go away from that, seems like a rather obvious odd distribution of spin states. What's going on?
I forget how I took this picture. It's to show you that we can measure the 7 spin states, but maybe RF, maybe this is part of, I will show you some cases where we understand better, but here I forget. So the field of spin of physics is mature now and has been, for the moment, up to recently, only due to contact interactions. So the idea is that spin of physics, you can have non-trivial physics due to the fact that the scattering length can depend on the molecular channel of your atoms. So contact interactions is basically a way to describe van der Waals interactions. You model the C6/R6 by a contact potential, and the atoms interact through a molecular potential, and the scattering length can depend on this molecular potential. So to make things clearer, if you take, for example, 2 chromium atoms in state ms equals -2, these two-body state can be described as a linear superposition of an S equals 6 potential and an S equals 4 potential. And if the scattering length in S equals 6 and S equals 4 are different, if you prepare this initial state in -2, -2, you will have spin exchange collisions, creating a pair of -1 and -3 particles, and the rate at which this spin exchange interaction happens is only set by the difference in scattering length between A6 and A4. So for example, this very simple formula describes spin exchange between -2, -2 and -1, -3. It can be seen as a beating effect in the mean field of the S=6 atoms and the S=6 pairs and the S=4 pairs. So for example, this is something you can observe in the experiment. In this experiment, which is in our group, we put many atoms in -2 to start with, and we observe spin oscillations, strongly damped, but we can still fit a frequency to that, a period to that, a quasi-period to that, and the period that we find is in a good agreement with the period that you have from this very simple equation. So this gives rise to some kind of weird magnetism where magnetization is constant because everything is in the central potential, so the magnetization of the system is constant, but you can still study magnetism. And because the magnetization is constant, the linear Zeeman effect can be, in fact, gauged out of the system, and it doesn't matter in the physics. And once more, I said that spin-changing collisions, finally, have no clear analog in spin 1/2 systems, because in spin 1/2 systems, you can change the spin state. The total population in -1/2 and +1/2 is constant in time. But here, you directly see spin exchange interaction by just measuring spin states and spin populations. So there's been a wealth of data on the spinor physics. For example, I think this is I forget where this comes from, either Chapman or Zengstock. I've seen a spin exchange, even in a group of Wolfgang Ketterle also. Coherent spin oscillations have been seen. And in this physics, it's interesting because, at the heart of spin exchange, there's a collision between here, for example, two m=0 atoms create a pair of 1 and -1. But as you see from this formula, this creates an entangled pair, in fact. So there's lots of quantum physics, in fact, that takes place during spin exchange experiments. And for example, the group in Hanover by Carsten Klempt tries to use this kind of phenomena to create twin beams and to use them for atom interferometry. So there's lots of interesting quantum effects. Another interesting feature is that you can actually really study magnetism. For example, this is a picture taken from the group of Dan Stamperkern, where you directly see magnetic domains in a rubidium BEC here. You can study magnetic domains, spin textures, spin waves. Some of the excited states have topological stability. So there's a nice experiment in a Korean group by Shin, who studies half vortices. So there's interesting magnetism study, and this picture is just to show you that you actually see spin domains, and this is really, we do study magnetism here. It is also a nice playground to study quantum phase transition. So this is a picture taken from the Paul-led group here at NIST, where by changing the quadratic effect, you can see the change, a phase transition here. And so it's a nice playground for quantum phase transitions. So this is all with bosons. But of course, now people are more and more interested in doing similar physics and similar studies with high-spin fermions. So for the moment, high-spin fermions are mostly studied in a group by Klaus Zengstock in Germany with F=9/2 potassium atoms. He sees beautiful spin oscillations, spin waves. It's a very interesting experiment. The interesting in high-spin fermions also is also that some of the high-spin fermions have some kind of SUN symmetry. So this is a subject, one of the favorite subjects of Alexei here. But new symmetries in the system arise, and then if you have new symmetry, you can get new physics. For example, it has been shown with ytterbium atoms that some of the spin degrees of freedom can store some entropy and create a system with less mechanical entropy, orbital entropy, in a scheme following the Pomeranchuk-like cooling. And our interest in this field is to study similar physics with a species with dipolar interactions. So to summarize this introduction, the main ingredients to study spin of physics is that you need a large spin, 1 or 2. And because of this large spin, in this large spin, there's spin-dependent contact interaction, which drives spin exchange that you can study. And for the moment, mostly with alkalis, what has been studied is physics associated to the interplay between spin exchange interactions and the quadratic Zeeman effect. Within this field, there's many new features with chromium atoms, which we do. So it's the first S equals 3 spin. So there are 7 Zeeman states. There's more. There are 4 molecular potentials, 4 scattering lengths. There's new structures that can happen. The spin-dependent contact interaction is very strong in the case of chromium atoms. And we have a purely linear Zeeman effect. There's no quadratic Zeeman effect. So in fact, this is a weakness of chromium atoms, I believe. But, so I will come back to that later. And the main and the biggest specificity in our experiment is that we have dipole-dipole interactions in the system. So what do dipole-dipole interactions change? So first, why do we have large dipolar interactions? We have large dipolar interactions because we have a large electronic spin. So because of this, so the large electronic spin comes from the fact that we have 6 electrons in the outer shell of the atoms whose spin is aligned. So there's 6 Bohr magneton dipole moment. And as a consequence, there's 36 times stronger dipolar interactions than in the case of alkali atoms, for example. So this dipole-dipole interactions is both long range, 1/r³, and also anisotropic. The dipoles repel if they're like that, and they attract if they're head to tail. And in the case of chromium atoms, typically, a way to characterize the strength of dipolar interactions is to scale them to the usual van der Waals contact interactions. And typically, in the case of chromium, the rate between these two interactions is 16%. So it's not a strongly dipolar gas. Dipolar interactions don't dominate, but it's not negligible. And I should stress, I think many of you know that, but there's only few experiments worldwide with non-negligible dipolar interactions. There is one in Stuttgart, in Innsbruck, in Stanford. There's also an activity with dipolar molecules in Boulder. But there's very few groups in the world that actually can study dipole-dipole interactions in a BEC. So there's 2 main features associated to dipolar interactions within this field of spinor gases. The first feature is that the magnetization is now free. And this comes from the fact that the potential of interactions between the atoms is not central anymore. So there's some kind of angular dependence. And as a consequence, the magnetization can evolve in time during a collision. So to see that, for example, there's this very simple classical picture. You have a first atom which radiates a magnetic field, which has some inhomogeneous structure. And then the second atom nearby can actually undergo Larmor precession and change its spin orientation. So as a consequence, you can have a collision where an atom in, say, m equals 3 here goes to m equals 2. And the typical time scale to have this spin-changing collision, which changes magnetization, is directly set by dipole-dipole interactions. And the second feature is a non-local coupling between spins because there is long range, there's 1/r³ dependence. So the first main feature is we can study now spinor physics with free magnetization. So without dipolar interactions, we have spin exchange at constant magnetization. But with dipolar interactions, you can have spin-changing collisions this way. And this is interesting because if there's a change in the projection of the spin state, because of the conservation of angular momentum, rotation should go somewhere. There's basically some kind of nonlinear intrinsic spin-orbit coupling. And after the dipolar relaxation, basically the 2 particles should start rotating around each other. This has interested theorists, many theorists in the field, because if it can lead to the spontaneous rotation of a BEC. And if this occurs at low enough energy, then you can have a situation where there's a spontaneous apparition of vortices in the BEC. So to see these vortices in the BEC, what do you need? You need that the energy released in dipolar relaxation matches the energy to nucleate a vortex, okay? But the energy that is released in dipolar relaxation is directly set by the Larmor frequency. So you need the Larmor frequency to be very small. Basically, you want the Larmor frequency to be so small that it's equal to the frequency of the vortex. And as a consequence, for this kind of experiments, you need a very good control of the magnetic field. Typically, you need a magnetic field control to the 100 microgauss level, or even better if you want to see vortices. So it's challenging from the experimental standpoint, but it's not unfeasible. And the second, as I said, the second main feature of dipole interactions is that it introduces long-range coupling between the atoms. And I will show in this talk that this has very good implications for lattice magnetism, also for spin domains, and part of the talk will deal with this spin-spin interaction from one lattice site to the next with chromium atoms. Okay, so after this introduction, I will first describe spin-off physics of a Bose gas with free magnetization in the bulk, and then I will describe similar physics in optical lattices. So if you prepare a cold cloud of chromium atoms above the critical temperature for BEC, and you work at a magnetic field close to the temperature, the energy of the Laburthe frequency is close to the kinetic energy, then what you see is this is an experimental picture. This is spontaneously you have a Boltzmann distribution in the different spin states. Basically, the kinetic energy is enough that the atoms can actually climb the energy ladder, the magnetic energy ladder. You have a Boltzmann distribution in the spin degrees of freedom. You can fit a temperature to this Boltzmann distribution. So you have a spin temperature, and our data shows that the spin temperature that you have is in good agreement with the temperature that you can measure by just letting the atom go and measuring the momentum distribution of the cloud. So this means that the spin temperature in our system can equilibrate with the mechanical degrees of freedom. An interesting and kind of funny thing happens once you reach the critical temperature for BEC. So this is the spin distribution that you get above TC for Bose-Einstein condensation. If you go below TC, all of a sudden, boop, there's a bimodal spin distribution. So all of a sudden, we have more m equals minus 3 atoms than what the Boltzmann distribution predicts. So this is this came as a surprise first, but in fact, it's quite easy to understand why this is the case. So basically, what happens is, what is BEC? It's the spontaneous accumulation of the atoms in the lowest energy state in the system. And in any finite magnetic field, the lowest state in the system, in the case of chromium, is m equals minus 3. So what you see is, in fact, the spontaneous accumulation of the atoms in the lowest energy state of the system, which is a ferromagnetic state. And as a consequence, the cloud spontaneously polarizes at BEC. So this is shown also in these two pictures taken at 1 milligauss, typically. When you reduce the temperature, you see the appearance of a condensate fraction. And when the condensate gets very large, all of a sudden, the magnetization per particle of the gas gets very close to minus 3. So this, in fact, shows that a non-interacting BEC is ferromagnetic. And it's a different magnetism from what you have in solid-state physics typically, where, for example, you have a BCS pairing and you have a singlet pair. Here, we have ferromagnetic BEC, ferromagnetic superfluid.
Now, when you say a non-interacting BEC is ferromagnetic, that sounds a little odd.
It's a way to present things. It's just to say that if you have the state wants to be in the lowest energy state, and in a finite magnetic field. So I'm talking about finite magnetic field because always experimentally zero magnetic field is not very well defined. But for a finite magnetic field, there's a well-defined state towards which the atoms want to go.
Right, but in order to get there, it seems like they have to have interactions to
Okay, yeah, sure.
The conservation of magnetization.
Yeah, so I assume that there's enough collisions and that you actually reach thermal equilibrium. And then I neglect the interactions in when I calculate the partition function and everything. But you're right, it's always the same. And I know that you had a talk by Zoran 2 weeks ago, and he enters in lots of details about this thing. So, but I mean, this is less. This is more trivial. What I'm saying. It's just that if you do the theory of a non-interacting BEC, you will find it's ferromagnetic, and this is kind of what we see here. So, in fact, I've tried to convince you that a BEC is ferromagnetic, but now I show you that a BEC is not ferromagnetic all the time. And this is the previous data that I showed. I lower the temperature and I see the spontaneous magnetization of the cloud. But if I operate at much lower magnetic fields, at 100 microgauss, the magnetization of the cloud remains very different from -3, although at this temperature, I get a condensate fraction which is 80% or more. So this means that at 100 microgauss, the cloud, the BEC, we have a BEC, it's 100%, almost 100% BEC, but the BEC is depolarized spontaneously. So as I tried to convince you that a non-interacting BEC is ferromagnetic, as a consequence, I claim that this effect that you have, the presence of a non-magnetized BEC, is necessarily an effect that comes from interactions between the particles. So in fact, it's relatively easy to understand why a chromium BEC is not ferromagnetic at low magnetic field. If the large magnetic field, it's clear that all the atoms want to be in the lowest energy state, in state m equals -3 here. But if you lower the magnetic field and the Zeeman energy is much smaller, then the atoms in -3 can have enough interaction energy to climb the magnetic energy ladder that you have here. More accurately, if all the atoms are in -3, then the only scattering potential that they meet is an S equals 6 scattering potentials. But if the particles go to -2, two particles -2 fill both the A equals 6 scattering length and the A equals 4 scattering length. And as a consequence, you can see that below a certain critical magnetic field, which depends as A6 minus A4, it's energetically favorable for the atoms to depolarize. And indeed, there's a very good agreement between the field below which we see demagnetization and this critical field for demagnetization. So this critical field had been predicted by these two theory papers. In fact, they're here, and also by the group of Daimler. So this is the phase diagram, which is expected in the case of chromium. If the magnetic field is very large, the BEC is supposed to be ferromagnetic. So there's an abscess here, which is A0, which is not known in the case of chromium. But what we think happens is we go from the ferromagnetic state, and we lower the magnetic field, and we start entering those non-ferromagnetic phases. In these theory papers, all the phases are calculated neglecting dipole-dipole interactions. So all these phases depend on the different scattering length that you have in chromium. But if you go from a ferromagnetic state to a non-polarized state, the magnetization has to change. So to be simple, what we think happens is that the phases are mostly set by contact interactions, but the dynamics to go from one phase to another phase has to come from dipole-dipole interaction. And in fact, we've checked that the time scale typically is related to dipole-dipole interactions. So we think we understand some of it. There are things we don't understand. So this is the picture that Bill was asking about, in fact. So this is, in fact, the spin state that we observe at low magnetic field for chromium BEC. And as you can see, this spin state is clearly depolarized, but it's quite different from what is supposed to be the lower state in energy in this polar state, where all the atoms should be either in +3 or -3, or this so-called cyclic state, where all the atoms should be in -3 or +2. So what we have is a depolarized BEC, but it doesn't match the mean field predictions that have been calculated. What we think happens is that if you do the mean field calculation here, you will find lots of local minima. And it's in fact very hard for the system to find a truly ground state, the true ground state of the system. So probably what happens is that we are kind of locked in a metastable spin state, and we cannot in fact reach this true ground state of the system. We are having a nice discussions with Brejvik and Marius Gajda. It's not completely clear what the dynamics sets the transition here. And it's possible that thermal excitations, in fact, play a quite important role in the dynamics. We are slowly continuing this work, but these experiments are very complicated because you need a very good control of the magnetic field, and to do systematics is quite demanding. Our idea to go deeper into this physics is to simplify a little bit the system, and we've built a new 2D trap. So the idea is that now we have the 2D trap ready. We have a 2D BEC, and we can now measure directly the spin domains in the 2D trap. And the interesting of the 2D geometry is that you can actually tune, if this is the 2D gas, you can tune the role of dipole-dipole interactions by changing the angle of the magnetic field with respect to the 2D gas. So this is something that we want to do in the near future, but we haven't made progress in this direction yet.
Now that's 0 temperature, right? The phase diagram.
The phase diagram is 0 temperature. zero temperature and also zero dipole-dipole interaction. So in fact, there's lots of, for theorists in the room, there's lots of room for, I think there are still open questions from even from at the mean field level, from the theoretical point of view. What is the phase diagram in presence of dipole-dipole interactions? Because as I explained, there is spin-orbit coupling in the system. So it's quite complicated. For example, if you're a theorist and you want to calculate the spin-off phase diagram, the first thing that you will do is a single mode approximation. That's the simplest thing to do. But here you cannot do that because there's a coupling between the orbital degrees of freedom and the spin degrees of freedom. So it's in fact quite complicated to study the phase diagram, even at the mean field level, including dipole-dipole interactions. So now comes the part where I talk about optical lattices. So I will do similar physics, but within an optical lattice. So we load the BEC into a 3D optical lattice, which is a kind of a weird architecture, but you don't really necessarily have to understand it precisely. It's a 5-beam optical lattice, and we operate in a regime where we lose a diffraction pattern. We can recover it if we lower the lattice. So we are in a Mott state where we have a core with 2 particles per site and a shell with only 1 atom per site. So, and the idea is, the question we want to raise is it possible to study quantum magnetism with dipolar gases? So as I explained earlier, quantum magnetism is described by an Heisenberg model of magnetism, which is an effective spin model with an Ising term and an exchange term. Now what we have in our system is dipole-dipole interactions between real spins. And if you write dipole-dipole interactions with quantum operators, you will find the same structure that is here, the Ising and the exchange term, but also additional terms. Within these additional terms, you've got this S1 minus, S2 minus terms, which are nothing but the magnetization changing collisions, which I've described in the first part of the talk. So we've studied these magnetization changing collisions in the lattice, and they play an important role. For example, imagine you put all the atoms in state ms equal +3 here, and you do that in this regime where you have 2 particles per site in the center. Now you vary the magnetic field, and you measure, as a function of the magnetic field, the number of atoms falling to m equals -2, or remaining in m equals +3. And you will see that there's no spin dynamics except for a given magnetic field. And this magnetic field corresponds to the following situation. The energy released in dipolar relaxation exactly matches the band excitation in the system. So we believe there's interesting physics because we operate in the Mott state, and all of a sudden there's a nonlinear coupling to an excited band where there's more tunneling. So there's some kind of nonlinear spin-orbit coupling in the system. And so we believe this might be interesting to study that. But another interest is that if you stay away from these resonances, basically magnetization is conserved. And you can actually ignore those magnetization changing collisions. So if you ignore those magnetization changing collisions, you can show that the effective Hamiltonian that describes the system, in fact, is different from the Heisenberg Hamiltonian for magnetism, but has a similar form, plus an anisotropy, which reveals the anisotropy of dipole-dipole interactions. There's similar research with polar molecules. And with polar molecules, it's even better because by combining electric and microwave fields and so on and so forth, you can actually tune the strength of the Ising term and the exchange terms. And there's ongoing research in a group of Junier who start to study these exchange interactions with dipolar molecules in optical lattices. So what we do in our experiment is the following. The BEC is formed in -3. We load the optical lattice. And then I won't explain the trick, but basically we promote the atoms from -3 to -2. So we do some kind of coherent transition from -3 to -2. And we prepare most of the atoms in state m equals -2. So this is a spin-excited state. Then we remove what we call the quadratic effect, and we prepare the atoms in a spin-excited state, and we study spin dynamics from this spin-excited state. We can explore 2 configurations. Either we have a core of 2 particles per site and a shell of 1 particle per site, or we can, in fact, engineer a loss in the center of the cloud to remove all sites with doubly occupied sites. And then I'm sure that I have only the shell with singly occupied site with unit filling. So the first data I show is in this situation where I got got rid of all the doublons in the system. And it's interesting to work in this regime because any spin dynamics, even small, that you see, is necessarily the product of intersite coupling in the lattice. So this is the experimental data. So at the beginning, most of the atoms are in m equals -2. And then if you wait long enough, you have an increase of the population in state -3 and -1. So as there's no site with two particles, it's necessarily, and it was the first observation of intersite dipole-dipole interaction with spin exchange interactions. And this is a case where at two different lattice sites, two m equals -2 states interact and create a -3 and -1. And this, contrasted to the usual spin 1/2 system, this can already be seen, clearly be seen, just by measuring populations. So the time scale for the dynamics is typically 20 milliseconds, and it's faster than either the tunneling time or even much faster than the super exchange time, which is typically 10 seconds in our system. So this is the red dots are the experiment, and the blue lines are the theory, which is based on exact diagonalization of the model that we use on the 3x3 plaquette. So it's really hard to go to macroscopic systems from the theoretical point of view because the number of spin configurations that you have to take into account is huge, really. What we see is directly many-body dynamics because each atom is coupled to many neighbors, and you do have to take that into account in the simulation to account for the time scale that we have. So you can also do the same kind of experiments with the doublons, and then we see more complicated spin dynamics, faster. It's faster because we have a larger dipoles. We have two atoms, and in quantum mechanics, 3 + 3 can give 6 or 4, but it's always larger dipole-dipole interactions. So we have, so we also have this, but then, so this is a relatively nice experimental data. It's even harder to do the theory for it because you have even more spin states, and in fact, we couldn't manage to get a realistic model for this kind of spin oscillation data. So I want to raise the question because it's always interesting. We always claim we do quantum things and quantum magnetism, and I want to raise a few questions regarding how quantum is our quantum magnetism. So the hope is that we do quantum magnetism because we study the Heisenberg, something close to the Heisenberg Hamiltonian for magnetism, and there's beyond the idea of quantum simulations and things like that. But it's not because the Hamiltonian is quantum that the system is actually quantum. The Hamiltonian of the planet is quantum, but most of the life is classical, right? So this doesn't solve the question of saying that our system is actually quantum. Another simple answer to say how quantum this is quite basic, is that it's hard to do a classical model of our system because the first step is actually to create something which is a one-body quantum state, an m equals -2 state. And you cannot create this m equals -2 state by just rotating a classical dipole from -3. So in fact, we try to think of a classical equation to describe our system, but it's really hard to really do it because the initial state is really quantum. It's a one-body quantum state, but it's quantum. So I won't have very clear answers to this question, but a way to prove that the system is quantum, which I like very much, and we are discussing with Perola Milman at Paris 7th University, is to try and look for entanglement in the system. Because this system, S1 plus, S2 minus, this exchange term, should create a delocalized excitation in the system and should create entanglement in the system. And there's nice ideas based on the idea that you can have entanglement widthness in the system only based on global spin variables. We cannot actually measure spin by spin the spin state of the atoms. But for example, you can show that for any mixture of separable states, the variance of the spin should be larger than S. So if you measure a variance of the spin experimentally, which is below S equals 3 in our case, then this is a proof that there is some entanglement of the system. You haven't measured it, you don't know how much, but there is entanglement in the system. And we are actually looking into adapting this criterion to our observations. For example, this criterion for the moment is too, within our simulation, it's too difficult to beat, but we have hopes that we can find entanglement criteria for our system. Another answer to this question of how quantum this is the following. It's not exactly the same answer, but basically is what we see described by mean field theories or kind of many-body physics. So what I want to say is that the dipole-dipole interaction has this anisotropic character, and as a consequence, if you have a homogeneous system, if you integrate dipole-dipole interaction over the volume, you find 0. So there's no dipole-dipole interaction in a homogeneous system. So at the mean field level, dipolar interactions cancel out for an homogeneous system, and as a consequence, at the mean field level, any spin dynamics that you should see is necessarily a border effect, in fact. So this is true at the mean field level, but the many body, the Hamiltonian, the true many body Hamiltonian, in fact predicts, even for homogeneous system, a non-vanishing spin dynamics. So this can be understood from the following equation. Start from a system where all sites have a state m equals 2. If you apply this Hamiltonian to it, you will find that you create a state which is the following, where you have an excitation there's in the site ij, a 2-2 pair, which became a 1-3 pair. And then the rate at which this happens is directly set by the dipole interactions between I and j site. And as a consequence, you can show that the spin dynamics is non-vanishing, and in fact, the rate of spin dynamics is not set by the average of dipole-dipole interaction, but set by this formula, where it's the root, the sum of the square, the root of the sum of the square of dipole-dipole interactions that count. And in fact, this value is in good agreement with the time scale that we get from our experiment. So, so I want to sum up what we've seen. It's a kind of weird quantum magnetism system that we have, where we have 3 different exchanges in the system. We have the dipole-dipole interaction exchange. We have the spin exchange due to contact interactions, and we also may have tunneling-assisted super exchange. So the consequences for magnetic ordering, we will see, but I don't know, I mean, I guess what I'm saying is that we're not in the spirit of quantum simulation. We have a quantum system which is weird, and we try to understand it, but how relevant this is and to solid-state physicists, I just don't know. But on the other hand, you have competing exchange terms, and this could lead to interesting physics. I'm trying to go faster because I think I'm a bit late. So in this talk, I've studied bulk magnetism, new spin-off phases at low magnetic field arise, and lattice magnetism, where we've seen intersite dipole-dipole interaction from one lattice to a site to the next lattice site, and we can directly probe it by looking at spin dynamics in the system. This shows that despite the fact that the dipole-dipole interaction is relatively small, really truly new phenomena arrive because of dipolar interactions when the spin degrees of freedom are released. And this is mostly because we have this free magnetization, which is completely absent if there's no dipole-dipole interactions. We try to study effective Hamiltonians which are close to Hamiltonians relevant for quantum magnetism. And what we would like to do is to study similar physics using either chromium or strontium atoms, but fermionic atoms now, because it's clear that if you want to study magnetism and find relevant studies for the solid-state community, it's better to work with fermionic atoms. Okay, just before I conclude, I would like to describe a new kind of prospect that we are pursuing right now, is to study double-wave physics to study even larger dipoles. So the question behind is always the same: is it quantum or is it not quantum? And it's kind of expected. If you have larger and larger dipoles, the physics may be less and less quantum in the end. And I'm claiming in this talk that I can study quantum magnetism with large dipoles, but how large the dipole can be. So an extreme way to do that is to create a double well, which we've done. So this is the BEC loaded into the double well. And using RF trick, you can actually flip the spin only of the left atoms. And the idea now is to study the interactions between 2 extremely large dipoles. Each dipole localized in each site of the double well can be seen as a dipole with n times s, where n is the number of particles and s the spin of the atoms. And what we want to study is kind of giant spin exchange between these 2 dipoles. So this is what we would like to see. And what we see is nothing. Okay? So this is embarrassing, but I think we understand why we see nothing, and this, in fact, signals the difference between quantum magnetism and classical magnetism, in fact. So this basically is nothing as a function of time. This is magnetization per atom on the right well and on the left well as a function of time, so nothing happens. There's something slightly that happens, but it's not very interesting for you. So basically nothing happens, although we operate on a regime where the time is much larger than the time scale for dipole-dipole interactions from one site to the next site. So nothing happens. Why is it the case? So this tries to explain it. This is a new slide, so I apologize, it's not very clear. But if you have a spin 1/2 system and you have plus 1/2 and minus 1/2, the Ising term for elastic interaction is the same if the spins are like that or if they're like that. As a consequence, the rate of flip-flop between this state and this state is in fact the same as is directly set by the exchange term in the Hamiltonian. So basically, all spin dynamics is set by the exchange term, and the Ising term actually doesn't play any role in this spin dynamics. If you start to have a larger spin, like what we have in S equals 3 in our experiment, you start with -2, -2. You see that we have seen exchange, but the exchange is in fact smaller. And why is it the case? It's because two dipoles in m equals -2, -2 times -2 is 4. But if they go to -3 and -1, -3 times -1 is 3, right? So the Ising term is in fact different in this spin configuration and this spin configuration. So you see that, in fact, now the spin exchange rate, or at least amplitude, will be reduced because of the Ising term. And now if you have a spin 10 to the 4 instead of 3, if you want to go from this large spin configuration to this spin configuration, the atoms need to go through all kind of series of states in which the Ising term, the elastic term, change. As a consequence, in fact, you can see from simple classical theory that the spins, in fact, are locked. And they remain like that. There's some spin fluctuations. They fluctuate a little bit, but mostly they're locked. And so basically, the interpretation of the thing is to say that if you go to larger and larger spin state, then the quantum fluctuations get less and less, in fact. So I guess the conclusion is not very positive. Is that you should beware of large spins. Sometimes we do good things and we see physics, which I think is quantum. But if the spin is too large, then you're screwed and you're back to a classical system. So with this, I thank you for your attention. This is the group of people having done the experiment. Mostly Aurélie, Amundsen, and Arijit have been involved. Also, I should Benjamin worked. He was a previous PhD student who did lots of work at low magnetic field with us. I want to emphasize a small workshop that we are setting up in Palaiseau this September, based on long-range interactions in quantum systems, molecules, Rydberg atoms, quantum gases, and so on and so forth. I know that Chris Monroe will have a talk there. And so this is the experiment, and thank you for your attention.